So the fact is that that problem I was fighting with last time, I really did need to consider the fact that the order did matter. So whether you picked the 1 first and then you got the 2 was different than if you picked the 2 first and then you got the 1. So if we looked at all those possibilities, we had 10 different possible combinations you could have done. So that if we would have found the standard deviation, which when you're finding that standard deviation, remember it's finding how far away from the mean it is, squaring those values and adding those together, dividing by n minus 1. So finding the standard deviation for each of those and adding those up, we add up to be 6. Well, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's only 9. I can't even count today. So if you take the sum of those standard deviations and then or the sum of the squares, I'm sorry, sum of the squares divided by the 9 that there was, we get our standard deviation to be 2/3. I was also having problems since I was already frustrated. Also having problems with finding I guess this is finding the variance because I didn't take the square root. So that's finding the variance. So the variance for the sample, so finding the mean of the sample variances was 2/3. If I found the variance of the entire sample, so finding the 1, 2, and 3, obviously the mean is 2 with those numbers. So finding the variance of the entire population, then you would find that difference between the value and the mean. So this one's 1 below. I guess I should have it as a -1 being squared. This one is a 0 away from the mean. This one's 1 above. Squaring those values, adding that up was 2 divided by the entire sample or entire population of 3. It gets to be 2/3. That's the variance. And the reason I was frustrated last time is I was looking at my calculator and it tells me my standard deviation. And I was forgetting to square that to find the variance of being the 2/3. So we end up with the mean of the sample variances being the same as the population variance, which is what I was telling you guys was true, but was not showing you to actually be true, which was really frustrating me. Questions? Also, if we looked at the distribution of those, so we had the first one was 0, and then 1/2, and then 2, and looked at all of these. Notice how, if we put all 9 of those values, this one is skewed to the right. That it does not give me a nice normal curve, because if it was normal, then these values would be over here, just right on the other side of 1/2, and so we would have this. But it's skewed to the right because my tail goes further to the right. Questions on those? Same thing with the proportion. If you found the proportion of 1s in each of these, so showing the 9 different combinations that we could have had, finding the proportions of 1, so this first one had 2 out of 2, so 1, and then 1 out of 2, and so forth. Finding the proportions of each, so those are each of these are different samples, so we're taking that population of 3 numbers, taking the sample size being 2, and every different combination of taking those samples of size 2, finding the proportion of 1s, adding up those proportions, and for being a sample proportion, that is our p hat, the sum of my p hats is 3. 3 out of the 9 gives me a mean of my proportions of 1/3. Well, obviously, if you've got 1 out of the 3, the proportion of the entire sample was 1/3. And so your population proportion and the mean of the sample proportions is the same. And if we showed that graph didn't turn out being a nice normal distribution, I don't remember why. Because that one should have been. I forgot to check on that part of things. Questions on that? So it really is fitting with what I was saying. I just knew I was having issues and couldn't figure out where my problem was. So now, are there questions on your guys' homework? So now this was taking the entire population and taking every single sample of the same size from the entire population and working with those, which trying to take every sample of the same size and trying to look at information from the entire population, not reasonable, because obviously if you've got the entire population, you're just going to find the population mean or just find the population standard deviation. You're not going to go through and find all these different samples of the same size and go through calculating them. But understanding that there really is that relationship between those two things, helps us with the central limit theorem as we start looking at having samples that we're going to work with and trying to use the samples to estimate what's going on with the entire population. So, the central limit theorem tells us that for a population with any distribution, the distribution of the sample means approaches a normal distribution as the sample size increases. So a lot of the stuff that we've worked with so far, we've always been working with starting with a normal distribution. This is saying it doesn't have to start off being a normal distribution. But if I'm looking at the mean of the sample means or the mean of the sample variances, that the central limit theorem can be used even when we don't have a nice normal distribution. That the distribution of the sample means approaches that normal distribution as the sample size increases. So these are the key things we have to be using the central limit theorem. First of all, the random variable x has a distribution which may or may not be normal, with a mean of mu and a standard deviation of sigma. So we know we've got a population. The population mean is mu, standard deviation sigma. The simple random samples, all of size n, are selected from the population. So we're making sure it's a good simple random sample. So our sampling techniques are important. That if you've got some sort of sampling technique that is not a nice simple random sample, that you may be skewing the data at this point. So you've got to make sure your sampling technique's good. All of your samples are the same size. So it's not like we're going to take one time we select 3 people, the next time we select 10 people, and we keep working with different sizes. They all have to be the same size samples. Then if we've met those criteria, then the conclusions are the distribution of sample means, so x bar, will, as the sample size increases, approach a normal distribution. So if your sample size is big enough, the distribution of your sample means will approach a normal distribution. The mean of the sample means will be the population mean, mu. So if your sample size is big enough, then you're going to have the mean of all those sample means will approximate the population mean. Also, the standard deviation of all the sample means is the population standard deviation divided by the square root of n. So, one of the things to keep in mind, the standard deviation does not approximate the actual standard deviation because we've already said that the distribution of the variances is skewed to the right, and the variance or the standard deviation is the square root of the variances. But we can kind of adjust things to where the standard deviation of all the sample means is the population standard deviation divided by the square root of n. So then, if we're looking at that combination of doing things. So the practical rules that we commonly use. For samples of size n larger than 30, the distribution of the sample means can be approximated reasonably well by a normal distribution. The approximation gets closer to a normal distribution as the sample size n becomes larger. So what we're saying is 30 is kind of the, I don't want to call it a magic number, but it's that really key number that we're looking for. If my sample size is 30 or larger, then we can pretty much just automatically apply the fact that the mean of those sample means will be this normal distribution. And so then we can apply the central limit theorem. If my sample size is smaller than 30, then we have to look at some other possibilities. But if the sample size is 30 or larger, larger is better. The bigger the sample sizes are, the closer it's going to approximate that normal distribution. But 30 is kind of that key number that we're going to look at when we're doing things. If the original population is normally distributed, then for any sample size n, the sample means will be normally distributed. So if you're starting off with something that you already know has a normal distribution, then you don't have to worry about is it 30 or more. You can have a smaller sample size. So for my population, well, I guess that's not really a great example, where we were just doing sample sizes of 2 numbers, those 2 numbers were going to be sample sizes of 2 because we had a normal distribution to begin with, could have keep being applied as we were doing things. If we were talking about heights of people has a normal distribution. And so since the heights of people have a normal distribution, we could select sample sizes of 15 people and find the mean height of those 15 people, and then find another sample of 15 people and the mean height of those 15. And if we did that with some sizes of 15, the mean of those sample means would be a normal distribution, even though we haven't hit that sample size of being 30 or larger. But the mean of my sample means would be approximating the population mean, and our distribution would be a normal distribution. But if you were talking about something that was skewed, let's go with grades and stats classes. Typically, the grades in my stats classes have got more people that are doing well and less people that don't do so well, and so my grades are skewed. And so if you're talking about percents versus A, B, C, D, if you're looking at those percents, it's skewed to where people are getting it's actually skewed to the left because you've got more people with that positive or higher values. Well, if I was taking samples of 5 students, I guess I can't do that. I would need to do samples of 30 students. So if you were taking classes of 30 or more people and looking at those, then taking the mean of all of those samples of 30 or more would give me a normal distribution. So the notation that we're going to use, the mean of the sample means is the population mean. This is what that's saying. This is saying the mean of my sample means. So if you're taking all the samples and finding the mean of those samples, the mean of the sample means is going to approximate the population mean, because mu is your population mean. The standard deviation of the sample means, so if you'd found the each of those sample means, or found the means and found the standard deviation of each of those sample means that we're looking at, the mean of the standard deviation of the sample means is the population standard deviation divided by the square root of n. This conversion is going to be one of those that we're going to need to be able to use. This is often called the standard error of the mean. Questions? Now, note that this applies to samples. We've got groups, not individuals. If you're wanting to look for the individual value, we did that back in section 3. When you know that you've got a group values, then we have to apply what's going on with this section and apply the fact that the group values are going to approximate the standard deviation, or recognize that the mean of those samples of the groups are going to approximate the population mean, and apply this to those kind of things. So there's a big difference between whether you're talking about groups of things or individuals as far as which one of these formulas we're going to apply. So if we look at applying something, if we look at number 14 on page 297. Designing motorcycle helmets. Engineers must consider the breadths of male heads when designing motorcycle helmets. Men have head breadths that are normally distributed with a mean of 6 inches and a standard deviation of 1 inch. If one male is randomly selected, find the probability that his head breadth is less than 6.2 inches. So because it's one male, then we're not applying anything we've learned that's new today. We're going to look at what we did last time, or last couple of times. So if I am trying to find the probability that one person's head, one man's head, is less than 6.2 inches. Now we know the mean. So first of all, we know this is a man's head has a normal distribution. We knew that it had a mean of 6.2, no, had a mean of 6, and a standard deviation of 1.0. I'm wanting to find the probability that his head is going to be less than 6.2 inches. First of all, if we're wanting the probability that's less than 6.2, we know 6.2 is a little bit above the mean. I'm wanting the probability that's less than this, so I'm looking for this area to the left. What did we do back in section 3? Okay, we need to convert it to the standard normal, and so we used our z-score is x minus the mean over sigma, and that is on your little reference sheet that you can be able to use to get that into your standard score. So in this case, what is 6.2 minus 6 divided by 1? Okay. So we get a z-score of 0.2. Now what? Okay, look on your chart. This is your z-score, so you're reading across the side and top. Will I subtract it from 1, or will I just use the number that's there? Okay, just use the number that's there because it's already telling me the area to the left. And what are you getting? Do you guys agree or disagree with Aaron? Hopefully you're agreeing because that is right. So the probability that one man's head is less than 6.2 inches is 0.5793, which is the same as saying it is 57.93% chance. Probability is of 57.93% that we're going to have a man that has a head that's less than 6.2 inches, a head breadth that's less than 6.2 inches. Okay, now if we look at part B, the Safeguard Helmets Company plans an initial production run of 100 helmets. Find the probability that 100 randomly selected men have a head breadth less than 6.2 inches. So now it's not just saying the probability that one guy's head is less than 6.2 inches. I want to know the probability that the group of 100 people has an average head breadth that's less than 6.2 inches. And so I'm wanting to find the probability that the mean of my sample mean is less than the 6.2 inches. Actually, I just want to, let's go ahead and do, the sample mean is going to be less than 6.2 inches. That would just be the sample mean I'd be finding here. Now, we need to remember that we've got 100 men in our group. Now, first thing I have to do is still convert it into a z-score. What will I use from you? What is the mean of the sample means? Population mean. What is the standard deviation of the sample means? Population standard deviation divided by the square root of n. And so when we go to calculate this out, we're still going to use the same mean that we had before, but when we talk about trying to find the standard deviation, it's not going to be the same as the population standard deviation. It is the population standard deviation divided by the square root of n. Because if you think about it, if you're taking one guy, if you get a guy with a big head or a guy with a little head, it's going to just have extreme differences when you're talking about individuals. But if you take a sample of 100 guys, and you're going to have some people with big heads and some people with little heads, and they're going to kind of average each other out. That when you take the mean of 100 people, you're not going to have as much variety. The extremes are going to get counteracted already. And so those are going to kind of take that variance and really limit it down a lot. And so as we go through doing this one then, the standard we already know that the mean of the sample means is the population mean, which was the 6.0. The standard deviation of the sample means is the population standard deviation divided by the square root of n, which is the 1 divided by the square root of 100, which is going to be 1/10. Questions there? So we've got a lot less variation between these different sample means. If we're looking at the size of 100 in our group. So when I go to find my z-score, I'm going to take the 6.2 minus the 6 divided by the 0.1 this time. So you're going to get a z-score of 2. So when I'm looking at it, even though it's a normal distribution, this one's going to have a lot less variation. It's going to kind of jump up, but it's going to be a lot skinnier. And so when you're looking at this, we're still having our mean of 6, but our standard deviation is going to be 0.1. And so we're wanting to find when the z-score is 2, and we're finding the probability that it's less than that. So we're finding the probability that x is the sample mean is less than 6.2. It's the same as finding the probability that z is less than 2, which is what this time? 0.9772. Or 97.72%. So the probability that I'm going to find a mean of my group of 100 men having a head breadth that's less than 6.2 inches is at over 97%. So that's a really high probability that we're going to be having this group having an average head size less than 6.2 inches. So then on part C, the production manager sees the result from part B and reasons that all helmets should be made for men with head breadths less than 6.2 inches because they'd fit all but a few men. What's wrong with that thinking? Huh? Well, I mean, if I'm looking at finding the probability that I'm going to find a sample of 100 guys and having their average head size is less than 6.2 inches, is almost 98% chance. Well, then why should I make it any bigger than 6.2 inches? Well, yeah, but that's not a problem. What is the problem? If I'm finding the average of 100 men, what's going inside that group of 100 men? Is every man inside that group less than 6.2 inches? Probably not. But if we got a big-headed guy, we probably have a little-headed guy that's counteracting him. So just because big head and little head average out to be 6.2 inches, does the helmet fit both of those guys? No. Big-headed guy is not fitting into that helmet. So just because we've got an average head size of 100 doesn't mean that we're fitting everybody in our group. It just means that when you take all these different head sizes and find the average of all those head sizes, you're probably going to get an average head size less than 6.2 inches. But you cannot take the information you're getting from this and apply it to each individual. If I wanted to know how well it would fit the individual, then I need to do the test on the individual. And the average, if you're trying to find how many people are actually going to fit this helmet, that's your 57% of them are going to fit this helmet. Or 57.93% of them are going to fit that helmet. Because that's how many men are actually going to have a head size less than 6.2 inches. Does that make sense? So don't use my test for an individual or for a group to try to explain the individual. All I can do is explain groups of 100, and if I was to take 100 people and find their average head size, then that average head size being less than 6.2 inches is pretty high, because 6.2 inches is above the mean, and it's enough above the mean with that standard deviation they have that it's probably going to fit that group of them. So don't try to explain the individual using the group stuff. Questions on that one? Okay, as you can see, you can draw conclusions about samples but not individuals when you're using the central limit theorem. And that is a key thing on these, is to make sure that you understand what you can and what you cannot find. Let's look at another example. Let's look at number 12 on page 297. The effect of diet on the length of pregnancy. The lengths of pregnancies are normally distributed with a mean of 268 days and a standard deviation of 15 days. If one pregnant woman is randomly selected, find the probability that her length of pregnancy is less than 260 days. So if we know we have a normally distributed, we know the mean of a pregnant woman is 268 days with a standard deviation of 15. I want to find the probability that one woman is going to have her length of pregnancy is less than 260 days. Give you guys a moment to do this. Which are we using today's stuff, or are we using section 3 stuff? Okay, this is an individual. Do what we did back in section 3. On your calculator, what you got as the answer. That way I can just look at it and see. Yeah, just type what your probability is. Since you don't have a piece of paper out. No, that's fine. It's fine. I'm just wanting to see what you got as an answer. What you get as your z-score? It should be negative because you put your x first and your mean second. So just draw an arrow that say those guys are backwards, and then it'll just make that negative, which will change your answer. Do it. Just A for right now. So as you're finding your z-score, you should be taking the 260 minus 268 divided by 15 to get a z-score of negative 0.53. So it's the same. What is the probability that z is less than negative 0.533? Which, when you look that up in the table, we get what? 0.2981. Now, when we did section 3, we counted on our calculators for a lot of work. What are we finding on this one? How did we find it on this one? What would we type into our calculator? No, I want to know the whole shortcut. We went to some sort of button on the calculator and just put in the information and let it do everything. Where did we go? When you did your second in VARS and took it to your distributions, which one did we pick? I saw a couple of you doing it. Okay, let me ask this question. Did you do the normal CDF or did you do the inverse norm? Normal CDF is what you were doing this time. Because you knew you had a normal distribution and you were trying to find the cumulative distribution, in this case from the left, every time you're doing this. Now, what did we have to put into the calculator? What is my leftmost value? Okay, some really negative number. What's my rightmost value? 268. What is my mean? Oh, I just did that wrong, didn't I? Sorry, this is 260. Yeah, my 268 is my mean. Dyslexic. And what is my standard deviation? And when you do, you're going to get what? Questions there? So you get an answer that's close. There will be rounding error. On the test, I have both answers, so either, which one of these two you use will be right when you go to do it. Now, that's telling me that if you take an individual woman, the probability that that individual woman has a pregnancy that lasts 260 days or less is just a little under 30%. Now, part B on number 12, if 25 randomly selected women are put on a special diet just before they become pregnant, find the probability that their lengths of pregnancy have a mean that is less than 260 days, assuming that the diet has no effect. And when you do these kind of things, you have that assumption that, in this case, we're going to assume the diet has no effect on them. What is the probability that if I had 25 women that I'm going to have the average length of their pregnancy is less than 260 days? So what is the probability that the mean is going to be, the sample mean is going to be less than 260 days? What changed? We're doing it for a group, not an individual. So what is the major piece that just changed? Standard deviation just changed. Because now I'm not doing it for just an individual, I'm doing it for the entire group. And so when I go to do this, it's going to have a distribution that is a lot less variance in there. It's going to be a lot more tightly compacted in there. It's still going to have a mean of 268, but now the standard deviation was the standard deviation before divided by the square root of the sample size. This time I have 25 women that I'm putting in my sample. This one has a standard deviation of 3. So you should be getting a z-score of negative 2.667. So the probability that my z-score is less than negative 2.667 is what? So using your tables, looking at the z-score, so you'll be looking for negative 2.67. Okay. Should be the same thing getting off the table, isn't it? Okay. This table's also getting the negative 0.0038. Or not negative, but the 0.0038. So go ahead and use the calculator and then come to conclusions. What would we do with the calculator? Okay, normal CDF. What do we put as our leftmost value? Okay, because it goes to the left forever, so it's going to be a really negative number, something so extreme it couldn't accidentally happen by chance. Negative 999 would probably be more negative enough on this case. What do we put as the rightmost value? Okay, that is our 260. What is our standard deviation, or sorry, what's our mean? 268. What is our standard deviation? 3. You can type into the calculator 15 divided by the square root of 25. In this case, it comes out to be a nice friendly 3, and typing in 3 is no big deal. In some of these problems, when you get a standard deviation of like 15 divided by the square root of 4, it's going to be a really weird decimal, and I guess 4 won't work. 15 divided by the square root of 2, maybe. It gets to be a decimal that's not going to be an easy one to look at. I guess I forgot one really important thing. Could I even apply the central limit theorem this time? Because my sample size wasn't 30. Did I just waste my time on something I couldn't do? Why was it okay to have a sample size smaller than 30? Women's pregnancies are already distributed using a normal distribution. So since it was already normal, my sample size did not have to be 30 or larger. So it's okay to use this. When you use this onto the calculator, then we still get the same answer of 0.0038. Now, we just got through coming up with this problem that said we had a sample of 25 women. We put these 25 women on this new diet. And when we did this diet, we got these women to have a mean pregnancy that was less than 260 days. What's that say about the diet? We made the assumption that the diet had no effect on the length of pregnancies. It did have an effect. Is it a good effect? Do we want women to have shorter gestation periods? Preemies are not healthier. We want them to go full term. So what would you say about this diet? Stop it now. Don't encourage anybody else to do this. Whatever it is that they just made this change is not a good change. And they should not even continue their trials to show you how bad of a change this is, because it's definitely having a negative impact on these lengths of pregnancies. Because the probability that you're going to have a group of 25 women have their pregnant that are all going to be having preemie babies is less than 1% chance, less than around 1/3 of 1% of a chance. So it's a very small probability that you're going to get that to happen. And so in this case, we've really had an effect on it. Questions? Now, when you guys go to do the test, pay attention to the details. Are you dealing with an individual or are you dealing with a group? That will be a big problem to pay attention to. So if you go through the whole entire test and everything that you've been doing on the test, you just keep using the mean and the standard deviation that I give you, you better stop before you turn the test in and stop and think, I never did a group. I missed something somewhere. And go back and reread the problems and make sure it wasn't looking at groups of, in this case, 25 women that we've put together. If you're trying to make a conclusion about an individual, then we use what we did back in section 3, and we can make conclusions about the individual. If, on the other hand, we're talking about grouping things together and trying to make a designation about the group, then you have to use the central limit theorem. Now notice when we do this, we cannot take this information and pull back and say anything about the individual. Just because the group had a mean pregnancy level, a gestation length that was less than 260, does that mean there weren't some people that went and had longer than average, longer than needed? We could have had somebody that waited 270 days before they had their baby. It balanced out with somebody that had their baby very prematurely. And so those things are going to kind of average out. So you can't say anything about each individual in that group. All you can do is say something about the entire group. One thing we haven't done yet, and I want to mention for a review, If we look at number 18 on page 273, and this kind of is a quick review of a lot of the stuff we've already done. Find the first quartile, which is Q1, which is the IQ score separating the bottom 25% from the top 75%. And we're assuming that IQs have a mean of 100 and a standard deviation of 15 for this problem. So I want to find Q1. Q1 is what we're looking for, that first, which is the percentile separating the bottom 25% from the top 75%. Where do I even start? We're knowing that we had a mean of 100 and a standard deviation of 15. What are you guys coming up with? Okay. So we had two different ways we can go about doing it. You guys were using the calculator and using which piece of the calculator? Okay, inverse normal. So we know we're doing the reverse of using that normal distribution. So you're taking that z-score now, you're trying to convert it to a z-score and working our way backwards to converting this into the probability to find the z-score to work our way backwards. So what is the area to the left? Which one? 25%, so we'll put the 0.25 in. And then you put in the mean, which was? And the standard deviation of? And it gave you guys the, what was it, 89.98? 88? So 89.88. Now, in this case, you round to the same place values that your original data was rounded to. So since our data was to the nearest integer, we would round this to 90. So since our mean and our standard deviation were both integers, we're going to round to the same place value as what those already were. You can't get more precise than what we've already rounded to before. Now, if I had to do it by hand and I was just using the tables. So what we're looking at on the table is we have a normal distribution. The mean was 100. The standard deviation was 15. I want to find the lower 25%. So this is 25%. Where do I go with my tables? What am I finding first? Okay, find 0.25 in the body of the table and find the z-score that goes with that. Is everybody finding it? You guys agreeing with Nathan at all? I haven't heard very many people agree or disagree with you. I kept hearing you repeat yours, Nathan, though. So you're looking for the number closest to the 0.251 or 0.25, which 0.2514 is closer than 0.2483 is. So that's off by 17 100 or 10,000ths versus 14 10,000ths. And so you're doing the coming over here to read the negative 0.6. And then getting that next decimal coming up to the top. So you're getting the negative 0.67. So this is telling me my z-score is negative 0.67. How do I change it from a z-score into the actual value? Still using that same thing we used before? So our z-score is the negative 0.67. I want to find my x value. My mean is 100. My standard deviation is 15. Multiply by 15, add 100. Simple algebra formula to be able to solve. And we still get our x value to be 90. So that 90, that score of 90, separates the lower 25% from the upper 75%. So people with an IQ of 90 or less are in the lower 1/4 of the intelligences, according to these values. I don't know that the mean, I know I've heard recently that the mean of IQs are actually increasing. Questions there? They're pretty close to being right there at that lower 1/4 of them. Considering the fact my mean and my standard deviation are both rounded, our cut score is not a set in stone perfect cut score. And since you're going to have a little flexibility anyhow, so you'd still consider them in the lower 1/4. And IQ scores, I think, are something that gets rounded to the nearest integer anyhow. I've never heard anybody say I've got a 121.5 IQ or something like that.